calculate the de Broglie wavelength of A, 2 kilovolt photon, and B, 2 kilovolt electron. Okay, first of all, look at the what the question asks. He asked for the de Broglie wavelength. So definitely we know the question wants us to find the lambda. Okay, want to find the wavelength. First of all, I want you to look at the unit. The unit is kilo electron volt. So what does it mean? What does it mean by kilo electron volt for both? So kilo electron volt is actually a unit for energy. Remember, we have two units for energy. We have electron volt and also joule, isn't it? Both of these, they are unit of energy. Both of them are unit of energy. Okay. So now, so we know this question provides us with the energy, and then we need to find wavelength. So how? What formula can help us to find the wavelength from the energy? Okay. So, but the first thing is we don't want electron volt. We want all the energy in joule. We want all the energy in joule. Why? Why we want energy in joule? Because later we're going to use in all the formula. All the formula here require SI unit. We only want SI unit. Okay. Okay. So first, let's talk about how to convert from electron volt to joule. Okay, from electron volt to joule is multiplied by electron charge. We want to remove the electron, we multiply the electron charge. If we want to convert from joule back to electron volt, we divide lah. We divide electron. But now it is kilo electron volt. So kilo electron volt, how? How to convert kilo electron volt to joule? Kilo electron volt add extra step. We want to remove the kilo, isn't it? Maybe I should put on the top here. Okay, better. Okay, over here. Yeah. So now I want to remove the kilo. That means I don't want the kilo. I want to remove the kilo. I multiply kilo. Multiply kilo. Yeah, kilo is exponent 3. Okay, if I want to convert from electron volt back to kilo electron volt, I divide kilo. Understand? That's it. So if I want to convert from kilo electron volt to joule, I multiply kilo, multiply electron charge. Then I get the answer. Okay. So first of all, I need to convert. Because kilo electron volt is not SI unit. It's not SI unit. What I need is SI unit before I can substitute into all the formula. Yeah, before I can substitute into all the formula. So I need to convert this kilo electron volt to joule first. So okay. So how to convert this 2 kilo electron volt to joule? So how much energy does this photon has? Let's look at the question A. So this 2 kilo electron volt is how many joule? Let's calculate. Okay, let's calculate. So energy for 2 kilo electron volt. So how to convert to joule? Again, how to convert to joule? I remove the kilo, multiply kilo. Yeah. So here I put 2 multiply kilo. Multiply kilo is exponent 3. Okay. Then I don't want the electron, isn't it? I don't want the electron. I multiply electron. Multiply electron is multiply 1.6. Okay, 1.6 exponent negative 19. The charge of electron. Okay. So this is this one is the multiply kilo, and this one this one is multiply what? Multiply electron charge. Okay, multiply kilo. This one I multiply kilo. This one I multiply electron charge. Okay. So after that, I surely get the unit in joule. All right. So what answer do I get? Yeah, what answer do I get? So after I multiply all these, okay, let's use the calculator and see. 2 multiply 1 exponent 3, okay, multiply 1.6 exponent negative 19. So I get the energy of photon is 3.2 exponent negative 16 joule. Okay, negative 16 joule. So I already get the energy in joule. Remember, always turn to SI unit before you substitute into any formula. Okay, we don't want kilo electron volt. We only want SI unit. Make sure you convert everything to SI unit first. Convert everything to SI unit, joule. Okay. Now already have the energy in joule, so I think the electron also 2 kilo electron volt should be the same energy. So I can carry down the energy for electron is also 2 kilo electron volt, which is also 3.2 exponent negative 16 joule. Okay, that's the in unit joule. In unit joule. Now once I have all in SI unit, I have the energy in SI unit, I can substitute the energy now into the formula. If it's still in kilo electron volt, you cannot substitute into the formula. You must make sure you already turn to SI unit, joule, then only you substitute into the formula. Okay, if not, you get the wrong answer. Now let's look at the photon. What formula for energy of a photon? What is the formula for the energy of photon? E equal to hf. Still remember? How about the electron? What is the formula for energy of an electron? The kinetic energy, which is half mv square. Still remember about this one? I did tell you. For the energy of a photon is E equal to hf. E equal to hf. We have a frequency, or we can say hc over lambda. Sometimes you can use hc over lambda. So this is the formula to calculate the energy of a photon. And for the electron don't have the photon energy, don't have the photon energy, but it has the kinetic energy, half mv square, isn't it? E equal to half mv square, kinetic energy of electron. So for photon, I use E equal to hf. Photon, a particle of light energy has E equal to hf energy. E equal to hf energy. That means for one particle of light, it has E equal to hf energy. For one photon. Understand? For one photon. For electron, it has kinetic energy. For electron, electron is a negative charge, moving with certain velocity. It has a mass of electron, isn't it? It has kinetic energy, half mv square. Okay. So now the question asks to find the wavelength, isn't it? The question asks to find the wavelength. First, we look at the question A about photon. We want to find the wavelength of photon. The formula just now, the energy for photon is E equal to hf. We also can change to hc over lambda. This equation already have lambda. We can find the de Broglie wavelength of photon. We already got the wavelength here, and energy is provided 2 kilo electron volt. So we can straight away find the wavelength. This formula actually no need to use. We actually no need to use this formula. This formula actually also can be used, but I will explain later on. When do we use this lambda equal to h over mv formula? Later I will explain about this one. Okay, first I look at this one. Photon energy equal to hc over lambda, because here got lambda can help us to find the wavelength. So now just substitute the energy we got just now in joule. Remember, this energy must be in joule, in SI unit. You ask me why? Because this formula only in SI unit, because the h, the Planck constant, the h is in joule second. So your energy must also be joule. You understand or not? Your energy must also be joule. Cannot be the kilo electron volt. You must convert to joule. The frequency also in per second. That's why we cancel. You see, we cancel the second and per second. Both side is joule. You see that this formula, both side is joule, because the H is joule second. So the energy must be in joule, in SI unit, cannot be electron volt, cannot be electron volt. So first of all, if you just see the kilo electron volt, change directly to joule. Okay, so now I already got in joule. I can substitute and get the wavelength lambda. Okay, let's do it. My energy is 3.2 exponent negative 16 joule, and then my H is 6.63 exponent negative 34. This Planck constant you can find in the list of constant formula. List of constant provided. And then C is the speed of light, 3 exponent 8 over the wavelength. Divide by the wavelength. So cross multiply, I get the wavelength equal to, let me check the answer for the wavelength for photon. So for photon, I got the answer is okay, correct. It is 6.22 exponent negative 10 meter. All right, that's it. Okay, this one, just move it the other side. Okay, yeah, it is correct. 3.2 exponent negative 16, correct. 6.22 exponent negative 10, correct. Yeah, so that's the answer. Okay, that's the wavelength for the photon. All right, now what about this formula, the de Broglie wavelength formula, lambda equal to H over mv? Do we really need this formula? For this question, we don't really need this formula, but this formula still can be used for photon. You understand? Yeah, you understand me? This lambda equal to H over mv is actually H over momentum. So when do we use this formula, the de Broglie? This is the de Broglie formula. When do we use de Broglie formula for photon? Can we use this for photon? Can. The answer is can. You only use this formula if, let's say, the question asks you to find the momentum of photon. Give you the wavelength, it gives you the lambda of photon, and then you need to find the momentum of photon. You can find the momentum. Do photon has a momentum? Yes, maybe you ask me. Photon is massless, zero mass, isn't it? Zero mass. But why you say it has momentum? Very good questions. Here I show you. In classical, this is what I searched from internet. Yeah, in classical electromagnetic theory, light turns out to have energy. It has energy and momentum. So light has a momentum. Okay, light has a momentum, and this happens to be related to E equal to PC. What is E equal to PC? Well, it is actually the formula E equal to mc square. E equal to mc square. So you ask me, do photon has a mass? The direct answer is the photon has zero mass. Okay, zero mass. But although it has zero mass, but it is a bundle of energy. It is a bundle of energy. It doesn't have mass, but it has energy. But it has energy. Okay, it has zero mass. But it has energy. You understand? The energy itself actually is a mass. The energy itself actually is a mass, because due to the, it's called this, it has zero mass, but it has relativistic mass. What I can say is, because this is a relativistic formula, E equal to mc square, the photon has energy. Energy actually is a form of mass, because energy can be converted to mass. Energy can be converted to mass. in later you learn about this nuclear reaction, you will learn that actually a little bit of mass can be converted to a lot of energy. That's why they use uranium to bombard the uranium, and the difference in the mass has converted into a lot and generate a lot of energy. So what I can say is energy and mass, they are both interconvertible. Energy can convert to mass also can convert to energy. So you ask me, photon, do they have mass? I say the direct answer is photon has no mass, but it has energy, and this energy is actually another form of mass. So if do photon has mass? It has a mass, but in the form of energy. Okay, so we can say that this de Broglie formula, the mass here, if you want to relate this mass to the photon, we can say this mass is actually the energy mass of the photon. This mass refer to the energy of the photon. Okay, energy of the photon, and that's why the photon has a momentum. Okay, has a momentum. If we look at this formula, E equal to mc square, the momentum, we know that the momentum actually is mass times velocity. Okay, the velocity for photon, for light, is speed of light. So this equal to mc times c, isn't it? Mc times c, mc square, mc times c. So actually this is pc. Energy equal to pc. So you see, energy. So you can see here, the p here shows that the light has momentum. The light has momentum p. You see not? So that is what it means by this. You see, E equal to PC. So this formula actually E equal to PC actually comes from the formula E equal to mc square. We just substitute the momentum formula into mc square, and we got E equal to PC. And we got this formula equal to PC, showing that the light has both the energy and momentum P. So that light has energy E and momentum P. Okay, so this formula E equal to PC means the light has energy. The light has energy E, and also the light has momentum P. So this formula, this formula you can use to find the momentum of light also. This formula can use to find momentum of the photon, or you want to find the wavelength of the photon, also can. Okay, this formula is to find the momentum of photon or wavelength of photon. Okay, but in this question it is not used, because we just use the E equal to hc over lambda is enough. Okay, now let us move on to the electron. Let's talk about the electron. 2 kilo electron volt, we convert to joule already, which is 3.2 exponent negative 16 joule. So that is the kinetic energy of the electron. Remember, electron don't have the photon energy HF. Remember, for electron we don't use HF. We only use half mv square. Half mv square, because electron has kinetic energy. Okay, it is moving with certain velocity. Like this one. So this energy, just substitute inside this kinetic energy here, and we substitute the energy here. We can get this is the mass of electron, because this is electron, we use the mass of electron, and then find the velocity of electron. After we got the velocity of electron, we can use the de Broglie formula. This is the de Broglie formula. Substitute the velocity we get, and we can get the wavelength of electron. Okay, can get the wavelength of electron. That's it. So let us do it. This is 3.2 kinetic energy, 3.2 exponent negative 16, and then half m mass of electron is 9.11 exponent negative 31. We can get this value from the list of constant value, and then our V is equal to, let's find out our V. What is the V value? Okay, let us find out the V value. I don't have the V value here. Never mind, I can calculate myself. Okay, so what's the V value? Yeah, let me calculate. All right, so the velocity I get is equal to 2.6505, and then what is the exponent? 7 meter per second. Okay, this is the speed. Okay, now what is the wavelength? So just substitute, use the de Broglie formula here, substitute the velocity here to get the answer. Okay, mass of electron okay, after we substitute here, and okay, so now the answer is equal to 2.746 2.75 exponent negative 11 meter. Yeah, this is wavelength meter. So do I get the answer correct? Okay, so the first question is 6.22 exponent negative 10. That's correct. The second question is 2.75 exponent negative 11 meter. That's correct. Okay, so that's all for this question.